Determination of gravitational constant G with the Cavendish method. Here, a fine wire is connected with a negligible mass rod, and negligible mass rod is connected with lead a spherical ball, and there is also another lead spherical ball, lead spherical ball, and due to the gravitational force, the this balls attracted towards this lead ball, and there is a twist in the wire. And knowing the twist in the wire, uh, we can determine the restoring torque, and with the help of restoring torque and the force between these two balls, we can determine the uh, mm, uh, gravitational constant. So twisting torque equals to restoring torque, now equals to F into L by 2 plus F into L by 2 equals to tau theta, where tau is the torque and theta is the angle moved by the rod or ball. This implies FL equals to tau theta, equation 1. Where theta is the angle of twist of the wire and tau is the restoring torque per unit angle of the twist, also called torsion constant. Hence from 1 Gmm by d square into L equals to tau theta, or G equals to tau theta into d square by m into mm into L, where m is the mass of big ball and small m is the mass of a smaller ball. Theta is the angle twisted, and d is the distance moved by the ball, and L is the length of rod. Observation of theta enables us to calculate G from this equation. Since Cavendish experiment, the measurement of G has been refined and the currently accepted values is G equals to 6.67 to 10 to the power minus 19 Newton meter square per kg square. Now acceleration due to gravity of the earth and determination of the mass of earth. Earth may be considered as made up of concentric spherical cells with the smallest one at the center. Here the situation of Earth is shown, that is Me represent the mass of Earth. And the largest one at its surface. Consider a point P inside the earth at a distance r. The point P will be considered outside the cell for all cell whose radius is less than r. The cell with radius less than equal to r make up a sphere of radius r for which the point P lies on the surface. This smaller sphere therefore exerts a force on a mass m at point P as if its mass mr is concentrated at the center. Thus the force on the mass m at P is F equals to G mr m by r square, equation 1. For the cells of radius greater than r, the point P lies inside. So accordingly to cell theorem, it does not exert force on M. Let Me equals to mass of the earth, Re equals to radius of the earth, and rho is the density of earth. Then mass of earth Me equals to 4 by 3 pi Req into rho. This represent volume and this represent density. So volume density equals to mass, and MR, that is the mass of the a spherical a sphere whose radius is r, at equals to 4 by 3 pi rq into rho. Here it is considered that the density of earth is equal everywhere. Hence me by mr equals to req by rq. This implies mr equals to me into rq by req. Equation 2. Using 2 in 1, we get f equals to gm by r square into me by rq by req equals to gm me into r by rqe, or gmem by req into r. The acceleration experienced by mass m at p is a equals to f by m gme by req into r. Equation 3. If the mass m is situated on Earth's surface, then r equals to re, and in this case the acceleration is denoted by g. Hence g equals to gme by req into re equals to gme by re square, or g equals to gme by re square. This represents the acceleration at Earth's surface or near to the Earth's surface. G is a measurable quantity. Re is known, that is radius of earth is known, and value of g is calculated by Cavendish experiment, and so we can measure the mass of the earth. From this formula we can also measure the mass of earth, because g can be measured on the surface with experimental setup, and we know the g value of this g by Cavendish law, and we also know the value of re, so me can be calculated using this formula. Acceleration due to gravity below and above the earth's surface of earth. First, above the earth's surface, here the earth is shown, and we are taking a point at a distance h, and a point with mass m. R is the radius of earth, and h is the height from surface of the earth. Let m equals to mass of the body at a height h from earth's surface. Re equals to radius of earth, m equals to mass of the earth, and Fh equals to force on mass m. Then Fh equals to g MEm by r plus h square. Here this is m, point mass, and now this earth can be considered as point mass, because point m, this point is outside the sphere, so this sphere can be concentrated at center, and so distance between these 2 point mass will be equal to re plus h. So here we using the gravitational force formula gmem by r plus h ka whole square. The acceleration experienced by the point mass is gh equals to fh by m equals to gme by re plus h ka whole square. Equation 1. This is clearly less than the value of g on the surface of the earth, that is g equal to gme by re square. From 1, gh equals to gme by re plus h to the whole square equals to gme. We are taking re out of the bracket, so re square into under bracket 1 plus h by re to the whole square. This implies gh equal to g by, because gme by re square equals to g, so we have written g divided by 1 plus h by re ka whole square, and this can also be written as g into 1 plus h by re to the power minus 2. Equation 2. For h less than, very less than re, we can use binomial expansion formula, that is 1 plus x to the power n equals to 1 plus nx when x is very less than 1 and n negative integer or fraction. So applying this rule or this formula, equation 2 becomes gh equals to g into under bracket 1 plus minus 2 into h by re, or gh equals to g into 1 minus 2h by re. This is equation 3, and this gives the value of acceleration due to earth at a height h above the earth's surface, where h is the distance of point from the earth's surface, and g is the acceleration due to gravity at earth's surface. Thus equation 3 tells us that for a small height h above the earth's surface, the value of g decreases by a factor 1 minus 2h by re. Now below the earth's surface, consider a point m at a depth d below the surface shown in the figure. Here this point is shown. This is the earth, and we are taking a point p below the d to the earth's surface. Now this distance from p to o will be re minus d, and the radius of earth is re, and this spherical part has mass ms. Below the surface, the force on m due to the outer shell of thickness d will be 0. This is due to the shell theorem, and the mass m will be experienced force due to the sphere of radius re minus d. Let the mass of this sphere be ms, then ms equals to 4 by 3 pi re minus d ka whole cube into rho, or me equals to mass of the earth, then 4 by 3 pi r cube into rho. Hence ms by me equals to re minus d to the power whole cube divided by re to the power q. Equation 1. Thus force on mass m is Fd equals to gms into m by re minus d ka whole square by the gravitational force formula, equals to gm by re minus d ka whole square. We are taking this out of in this side, and into we are putting the value of ms from this formula, and ms here ms gm and re minus d by whole square, this part is here and ms is here. From this formula, re minus d by re minus d to the whole cube divided by re cube into me from 1 equals to gme into m by re cube into re minus d, or gme m by re square into 1 minus d by re. Hence gd equals to ft by m equals to gme by re square into 1 minus d by re. This implies gd equals to g into 1 minus d by re. This formula shows this gd represents the acceleration due to gravity below the earth's surface at a distance d, and g is the acceleration due to gravity due to earth at its earth's surface. Thus, as we go down below the earth's surface, the acceleration due to gravity decreases by a factor 1 minus d by re.